Well, I'd like to welcome everybody to the latest Sustainable Practice for Wisconsin Printers webinar, Take Your Money Back, Compressed Air Systems. Next slide, please. Program is brought to you by the Wisconsin Department of Natural Resources, the Green Tier Program, the SGP Program, Flexographic Technical Association, Great Lakes Graphics Association, SGIA, and then the Tag and Label Manufacturing Institute. Next slide, please. Your moderator today is Joe Lyman. I'm president of the Great Lakes Graphics Association. Next slide, please. Webcast logistics, a little bit about what we'll do today in terms of housekeeping rules. All attendants are muted. We do have opportunities for questions and comments. If you'd like to ask a question immediately, you can always submit your question in the box on the right side of the frame. If you'd like, you can also ask questions at the end of the program. Of course, this webcast is being recorded and will be provided to you in the next few days, and then the information will be followed by an email. Next slide, please. A little bit about today's agenda. We'll do welcome and introductions. We'll talk about the Sustainable Green Printing Partnership, the Green Tier Program. In terms of compressed air, we're going to talk a little bit about operational costs, energy saving opportunities, management strategies to reduce your energy use, and then leak detection program, and we'll case study quad graphics. And finally, we'll end up with questions and answers. A little bit about today's speaker. Tony Creel is a professional engineer and project manager at SCS Engineers with more than a decade experience specializing in facility energy related projects. His project experience includes conducting compressed air assessments, energy audits, and commissioning HVAC systems. Thank you so much for presenting today, Tony. Next slide, please. Talk a little bit about the Green Tier Program and SGP partnership we have with the Department of Natural Resources. The Wisconsin Green Tier Printer Industry Charter values partnerships among industry and the Department of Natural Resources and encourages certifications like SGP and Green Tier that support printers on their sustainability journey. Today's webinar is just one example of the Charter's work to help printers improve their sustainable business practices. Both Green Tier and Sustainable Green Printing Partnership programs offer Wisconsin printers the opportunity to reduce their environmental impacts and operational costs through a comprehensive sustainability or environmental management system to continuously improve performance. I encourage you to visit their websites and learn more about Green Tier and the SGP to help you grow your green bottom line. Next slide, please. At this time, I'd like to hand this off to Tony, who's going to talk with you about compressed air systems. Thank you, Tony.
Yeah, you're welcome. Thanks for having me on board today. I hope we can have a little educational session here and learn a little bit about what compressed air systems is, and maybe more importantly, how to get some money back from it. So let's start off. What is compressed air? Compressed air is a form of stored energy that is used to operate machinery, equipment, or processes. Compressed air is used in most manufacturing and some service industries, often where it is impractical or hazardous to use electrical energy directly to supply power to tools and equipment. It's powered by electricity. A typical air compressor takes approximately 7 volumes of air at atmospheric condition and squeezes it into like 1 volume at an elevated pressure. So we're looking at air at atmosphere, which is about 14.7 psi, and we're squeezing that down to 7 psi. To about 100, squeezing it to 100 psi. So we're taking this big volume and bringing it down to 1. The resulting high pressure air is distributed to equipment or tools where it releases that useful energy to the operating tool or equipment as it is expanded back to atmospheric pressure. Compressed air is often called the fourth utility because it is essential element to your business operational activities. It's so vital that the facility, cannot operate without it. So similar to electricity, natural gas, and water utilities, your compressed air system is something you have complete control of, and again, it's just as vital as those other three. So it's often termed the fourth utility. The system here, the compressed air systems consist of generally a supply side, which includes the compressors and air treatment, and a demand side, which includes distribution and storage systems and end-use equipment. A properly managed supply side will result in clean, dry, stable air being delivered at the appropriate pressure in a dependable and cost-effective manner. So those are some important things to keep in mind, is it needs to be dependable and cost-effective. A properly managed demand side minimizes the wasted air and uses compressed air for appropriate applications. Improving and maintaining peak compressed air system performance requires addressing both the supply side and the demand sides of the system and how the two interact. A modern industrial compressed air system is composed of several major subsystems and many subcomponents. Major subsystems here include the compressor, the prime mover, the controls, the treatment equipment, and accessories. And then, of course, the distribution system. The compressor is the mechanical device itself that takes that ambient air and increases its pressure. The prime mover powers that compressor. Controls serve to regulate the amount of compressed air being produced, and the treatment equipment removes any contaminants from the compressed air and accessories to keep the system operating properly. All right, so system efficiencies here. People often assume that because they breathe air that compressed air is free. Well, it is not. It is one where to compress the air, one would find that most of the electrical power inputted to compress that air is lost in the form of heat due to the physics and thermodynamics involved. Once the air is compressed, it must be transported and losses occur and inefficiencies arise along the way. So in the end, you're only getting about 10 to 15% of the original energy input that performs the useful work in a manufacturing process. So in other words, about 90% of the energy to produce and distribute that compressed air is typically lost, which makes it all that more important to think of compressed air as a resource for production, and that it might be the most inefficient source of energy in a plant. So again, compressed air is generally inefficient and can be expensive. If we were to think about it in terms of operational costs, how much does it cost to operate an average compressed air system? Well, a quick rule of thumb is that on average, it costs 7.6 cents per horsepower per hour. So again, what does that mean? It means it generally senses the input parameters is how big of a system you have. That's the horsepower generally of your air compressor system. If you take that and multiply it by the hours that you run it times 0.076, that's probably a good range in terms of where you might be in terms of how much you might be spending on your operational costs. So here's an example. Let's say we have just a 100 horsepower air compressor that generally runs for 2 shifts, so that's 4,250 hours in a year. You're likely paying in the range of $30,000 just to operate that compressed air system. Of course, if you have higher electricity rates or don't operate your system at full load or as often, then your annual cost would be a little bit different here. But in general, this is the range, that first cut range that we're thinking. thinking about here. The general rule of thumb is that you'll also generally spend or should spend about 10 to 15% of the initial cost of the system on annual maintenance procedures. So adding the two together, if we were to think about it over a life cycle thought process here, would account for about 90% of the total money that is spent compared to that original 10% of the initial installation cost. So when we begin to talk about operational costs, we would be doing ourselves an injustice if we didn't balance that discussion with other issues or concerns that O&M or management staff are concerned with. So that generally also revolves around reliability and performance issues, or the quality of the air that I'm getting out of my compressed air system. So again, we need to balance those concerns. It makes no sense to save on energy if the direct result is that we lose products and have to use that, if we have to use more energy and more materials to make that product again. So again, the point is that like the quality, we have some ways to manage our costs. Well, a compressed air system is one of those systems that needs its cost managed as well. So let's talk about the economics for management. That's usually one of the driving factors. So a lot of times we talk about it at the end, but let's talk about that at the beginning here. Talking about compressed air systems can be difficult if we're talking to management, and there are a lot of different ways where we can talk about the economics. So the most common one is a simple payback approach, where you get an estimate in terms of cost to upgrade the system versus the estimate in terms of how much it's going to save, and you divide the two, and you have a simple payback period. How many years or months will I see my money? When will I see my investment pay back? Another one is the net positive cash flow approach. Then the net positive cash flow analysis essentially looks at that monthly or annual energy cost savings of a project, and if they are greater than the finance payments, the project exhibits a net positive cash flow immediately and should be implemented. So a quick example is if you were to finance an energy conservation measure on your air compressor system that costs you $500 a month, but you're saving $600 or $700 a month, then it's again a net positive cash flow, and you're winning right out of the gate. But the one that I'll spend just a little bit more time and have an example here discussing is the revenue versus cost and profit analysis approach. Some companies let's say a company is working on a slim net profit of 5%, and they'd like to increase their net profit. Maybe that's an internal goal. There are generally two ways to do this. You either increase revenue by increasing sales, or you decrease costs. In the end, it works out to both increase in profit, right? So if your business were to look at reducing costs by implementing an energy project, that would save them $1,000 annually, for example. That would be equivalent to otherwise earning an additional $20,000 in revenue. So that, again, that's 1,000 divided by, our 5% net profit example here. So an energy efficiency project of this type essentially has that same impact on profits as increasing sales 20 to 1. If we were to look at the energy management hierarchy, where should we save, or where should we start? I like this graph because it's a classification of energy options that prioritized to assist progress towards essentially a more sustainable energy system. It is a similar approach to maybe some have heard about the waste hierarchy for minimizing resource depletion, and it adopts a parallel sequence. The highest priorities cover the prevention of unnecessary energy usage, both through eliminating waste and improving energy efficiency. So basically, what I'm trying to say is that the most cost-effective solution is to first turn it off if you don't need it. So this means looking at, your schedule opportunities first. We've seen a lot of folks not realize that their system has always been running over the weekends when no one is present or there's no shifts. But at some point, whoever was managing it thought we needed it on, at 5 a.m. when that first shift starts, so they left it on over the entire weekend. So again, that's the first part, is to be a little bit leaner. So switch it off, eliminate waste if you don't need it. The next step is to say that if we have to use energy, let's use it as efficiently as possible. So, and for air compressors, that usually means reducing air leaks, eliminating inappropriate uses, looking for alternatives in lieu of using compressed air, and installing variable frequency drives or VFDs for better control. So that's that keener section. The last priority here is, even though it may be, most talked about recently, is if you want to reduce your environmental footprint, is to look at renewable systems. I think they've been, previously discussed in other webinars in this series. So please go to there to learn more about renewables. But in terms of when we talk about cost effectiveness, turn it off, use it as efficiently, and then generate it as cleanly as possible is generally our energy management hierarchy. And usually renewables aren't part of something that we can generally control. But if it is, all the power to you. All right, energy saving opportunities. Let's get into it. Compressed air, is clean, readily available, and simple to use. And as a result, compressed air is often chosen for applications for which other energy sources might be more economical. But users should always consider more cost-effective forms of power before considering compressed air. Many operations can be accomplished more economically using alternative energy sources. Inappropriate uses of compressed air include any application that can be done more effectively or more efficiently by a method other than compressed air. So examples of potentially inappropriate uses of compressed air including having abandoned equipment that's still attached to the system, having idle equipment that is on that's not being used. So a suggested alternative to that use would be to potentially install a shutoff valve at the inlet process of that equipment and tie that back in to the operation of the equipment. You could have a timer installed if you needed that to be one of the first things to turn on, of course. Another potentially inappropriate use is cleaning up or drying or process cooling using compressed air, whereas a better alternative might be a low pressure blower, electric fans, or even brooms. Sparging, aerating, agitating, maybe you're dealing with some liquids. Sometimes we've seen compressed air being used for these applications. Well, maybe another alternative that's more appropriate would be a low pressure blower or a mixer. Padding is another one. Vacuum generating. If you're trying to do create a vacuum using a Venturi device, that's a very, very cost heavy system. It may be a dedicated vacuum pump for that simple application is more appropriate. Personal cooling. A lot of times we've seen people use that nice, cool, compressed air to cool themselves. Well, let's get an electric fan. Air motor driven equipment versus electric motor driven equipment. Pneumatic hand tools versus electric hand tools. A lot of technologies have increased related to our battery energy usage. So maybe an electric, hand tool with a battery is appropriate use here. So I guess in summary on this slide, as a general rule, compressed air should only be used if safety enhancements, significant productivity gains, or labor reductions will result. If compressed air is used for an application The amount of air used should be the minimum necessary, and pressure should also be used at the appropriate applications and for the shortest possible duration. Compressed air use should constantly be monitored and reevaluated over time. If we were to look at another great energy saving opportunity, we would evaluate our system leaks. Leaks can be a significant source of wasted energy in an industrial compressed air system, sometimes wasting 20 to 30% of a compressor's output. So a typical plant maybe that has not been well maintained or where they haven't conducted an air leak survey might have a leakage rate up to 40% of the total compressed air production capacity. On the other hand, proactive leak detection and repair can reduce leaks to less than 10%. While leakage can come from, any part of the system, the most common problem areas include couplings, hoses, tubes, and fittings. So that's where those push to lock fittings come into play. The disconnects, O-rings, that may have slipped off or were never installed to completely seal may be missing. Most applications that have an FRL, filters, regulators, and lubricators that weren't properly set up or have been neglected over time, they can be a high source of system leaks. Open condensate traps, if you don't know where yours is or what that looks like, that could be a source of system leak. Joints and flanges, which have always had a missed or defective weld, controls and shut-off valves where the more packing through that stem, that can be a source. And just odd or poorly maintained tools, the point-of-use devices, just over time, things get worn. So again, these are the common places where you might want to start looking to evaluate some system leaks in your system. If we were to associate our system leaks with the cost of a leak, I like this graphic here because it really shows that. Did you know that a quarter-inch leak can cost a typical facility $8,382 per year in wasted electricity? In addition, again, to it being a source of wasted energy, leaks can also contribute to some other factors that I'll get into. Not all leaks, of course, are round, but are in a circular. But this really shows that how leaks can really start adding up. $500 for 1/16 or 1/8 of an inch to $2,000 versus again a quarter inch, and you may have up hundreds of feet of linear pipe in your compressed air system, and a lot of joints. So there may be a lot of opportunities to evaluate where your leaks are coming from. Let me also add that the leaks can also cause a drop in general system pressure, which can make air tools function less, efficiently, adversely affecting production. In addition, by forcing the equipment to generally run longer, leaks can shorten the life of almost all system equipment, including the compressor package itself, right? Increased runtime can also lead to additional maintenance requirements and increased unscheduled downtime. And finally, leaks can lead to adding unnecessary compressor capacity. So if you were to want to look at your system and get a better idea, we would recommend that you start with a system level approach. So let me take a step back. So we've already established that compressed air systems are inefficient, expensive, and often misused. Taking a system level approach can help you analyze your needs and devise solutions to your challenges. System approach includes looking at the entire compressed air system from start to finish when considering optimization. So just looking at a single air compressor or an end use alone may be beneficial, but an individual improvement opportunity may be masked by a problem in another part of the system. The The best plan is to look at the compressed air system from the air inlet to the compressor all the way at the end of the use of the air on the plant floor, so and including everything in between. Taking a system approach can help eliminate ongoing system problems. For example, one plant had a history of poor air pressure on the plant floor, especially in the areas that were farthest from the compressor room. This plant had tried to remedy this problem by adding additional air compressors. At the time, they had, 1,000 horsepower worth of air compressors, but the poor air delivery performance problem persisted. So if you took a total systems review, you revealed that even though more air compressors had been added, the piping delivery system had never been upgraded. This plant was essentially trying to push 1,000 horsepower worth of compressed air through a piping system that was originally designed for 300 horsepower. But if they had taken a total system approach before adding the compressors, they would have realized that a piping system upgrade was necessary. So here I list the general steps when taking a system level approach. You want to develop a basic block diagram and a pressure profile. What does that mean? That means just taking blocks and here's where my air compressors are, how many do I got, draw a block, and trace the piping to my next system, whatever that may be, and trace that all the way down. You also want to, so that helps you get an idea of what your system actually looks like. Maybe you might be so lucky to have a diagram somewhere in your building documentation. Maybe not. Maybe this has to be created. Number 2 here, measure that baseline kilowatts and pressures and your leak load, and then calculate your energy costs. It's one of these things where you just can't manage it if you don't measure it. The next really quick thing is to implement an appropriate compressor control strategy. Make sure you understand how your compressors are operating. The analysis of different types is beyond this presentation here. Number 4 would ask you then, after you looked at your compressor control strategy, is then go back, remeasure, and recalculate after you've made some changes. Number 5 here would be identifying fixed leaks and correct inappropriate uses. Number 6, check for those opportunities to reduce costs and improve performance. And number 7 would be begin this implementation and continuous improvement process. And then maybe the most important part is to report the results to management. All right, so let's take what we've talked about here and look at a case study of where Printer did implement a leak detection program. And that also found some good value in implementing that leak detection program. First, they did notice that they had some of the common examples of waste associated with their high pressure air systems. And in this case, we're talking, 125 pounds per square inch. They left air running into pockets that they're calling, or into parts of their system that weren't in use. They found that, of course, they had employees using some of that compressed air for their personal cooling. They would use it to clean up after themselves. And again, so just to point out that using that high pressure air and where low pressure air application would work for them, for this case study, they calculated that their high pressure air was 6 times more expensive than their low pressure air. Again, it takes some energy to get up to 80 psi. It takes more energy to get up to 100 psi, and it takes a lot more energy to get up to 125 psi. And there's economies of scale that go into that. What you want to also do that they found was that their system had elevated pressures. The common solution is, if we don't have enough air, well, we try and think about raising the pressure set point. You can do that, but you should also look and make sure that the filters and regulators that ever drop to your pieces of production equipment are appropriately set. So that requires getting out the manuals and verifying what it's at. It might only be necessary for some of these to operate at 80 psi or 60 psi. But if you're operating at 120, why are you operating at 125 psi? And of course, the easiest one that they found was to turn air off to equipment when not in use. So what we got here is that, they installed an automatic solenoid valve that was tied in to their system. And I got a picture here coming up. It kind of looks like this. That solenoid valve shut down the main air to the piece of equipment after 30 minutes, if it didn't receive a run signal. They also have a flow meter attached in this application. Not every application needs a flow meter, but again, it's back to can't manage it if you don't measure it. What they find here is, once they did an air leak survey and had that system up and running, that 27 was a good number for their optimal application. That's the amount of flow they needed. Well, if that flow meter starts to increase, to 30 to 35 to 40, you're using a lot more airflow than what you had at baseline. So there might be a leak in the system. So it's good for a comparison between, like pieces of equipment. So what did they do? They did install a leak detection program. They created a statement of need to work with management where they wanted to reduce that system electrical consumption by identifying and repairing air leaks. Justification here was that they found out that their facility, operated approximately 1,000 horsepower worth of air compressors. So to put that in dollars, annually, that is in the range of $335,000 for their typical application. When I looked at all their energy usage, electrical energy consumption, that was about 14%. So it's a relatively big chunk of the pie when you start considering other HVAC, pumps, fans, lighting, other industrial process equipment. They found that their inappropriate uses of the high pressure air were costly. And so again, I said this before, but the General Industry Standard, for a well-maintained system, it has leaks at 10%, but they found that theirs were a bit higher initially, so they had a lot of opportunity. Let me give you one more example of, maybe just more compressed air economics here. Here's maybe a picture of a 200 horsepower high pressure air compressor, which consumed 170 kilowatts for every hour that they ran it, and they got about 900 CFM out of it at 90 psi. A pretty pricey piece of equipment when you consider how much it cost them just annually, $76,000. So again, just to try and reinforce that it is really a cost. So there's a lot of opportunity here. Now let's get back to their leak detection program and the components of an effective leak detection program. They want for every piece of equipment that you have scheduled maintenance tasks and that you have checklists that go in, that has someone who's experienced who looks at the piece of equipment all day, every day, that they actually go in and look at some different things. So it breaks it down into easy, quick checks. A good, effective leak detection program invests in leak detection tools. Generally, these are ultrasonic leak detectors that can find and usually measure the severity of the leaks. Training and labor is a very important part of an effective leak detection program. Certified operators trained in using the equipment and the frequency is valuable. And once you find it, that you fix it, right? Whatever your system may be, if it's fix it right away, or if you got put in a work order, that it actually gets done and that it actually gets fixed. And if you happen to have a priority system, one that weights it more than the other, you might be able to find and to fix the ones that are bigger leaks based on your application. Again, an effective leak detection program will measure it, and they'll determine the financial impact and awareness. And once you measure it, you can build your energy team and talk about it and help spread the message and teach production staff the value of energy conservation. So it can be a win-win if everyone's on board. So if we were to look at the checklist on something like this, this is an example of one where they go down. You might have a paper copy. This one was built into their maintenance system here. But what I want to do is get into maybe, back to the leak detection equipment. These ultrasonic leak detectors are important because in a noisy factory, and the environment is generally, it can be hard to hear just using your ears alone. In fact, approximately 80% of air leaks are not audible. The human ear cannot hear a lot of these air leaks. So 80% of the big ones that you hear when no systems are running, the plant's gone, everyone's gone, and you can walk in and you hear air hissing. Those are big leaks, but there might be only a couple of those. So these ultrasonic leak detectors can really help you zone in and verify that you're not leaking something out of something that you can't hear. There's a lot of different kinds. I'm not going. We've got a couple bulleted points here that there, and then there are a few different models out there. We're not here to advertise one or another. There's older ones, and I don't want to say older ones. I want to say analog ones that are just easy to use and just as good as digital ultrasonic leak detectors. And they're good at canceling out background noise. You might have digital ones that you can program and have an onboard memory capable of storing that data, and you can even download the data. You could have some that are good for performing other predictive maintenance tasks. So it could be dual purpose, right? But some might not be intrinsically safe to the operation that you're using. So that's something to be considered, to consider. And then similar to previous, there may be only one that is intrinsically safe, I guess is my point. Here's a picture of a ultrasonic leak detector in use. This one has a digital display that's showing a decibel level, and that you can point it and find that it's hearing it where you might not be able to hear it. And what they're using the new number here is just to kind of weight the severity of the air leak. Some might just have a bar when you use these pieces of equipment, and some might just and then you can make a priority, low, medium, high leak, or a low, medium, high priority. So again, this would be used in a tracking sheet. Sometimes these have headphones associated with them, so it really cancels out the background noise. Once you, of course, once you find an air leak, you should have some sort of a compressed air vacuum leak location tag where you can apply it to the piece of equipment. This is what this company uses here. Here's some more pictures of where they are checking the fittings and the gauges and getting into the system and checking it. Again, they usually find, once a trained technician gets going on a big system, that he finds typical applications and some repeat offenders, if you will. Here they do, identify it and fix those leaks using that take, or the seek and repair. Find it, fix it right away. It depends on your system, right, and how you want to go about it, and maybe the manpower hours that you're willing to invest. If we were to then, track it for management, management reasons, we would, make a spreadsheet. We would describe where the leak was it fixed, so we can track it, was the service order prepared, and then we would try and identify the leaks and the cost avoidance. The argument comes up here is, how long ago was this leak going on? Could you say that it's been going on for the last 3 months or 3 years? But if you then break it down, over a year, if we were to let this go, we could actually calculate how much this is costing us. And then we could talk about that in terms of what our return on investment would be back to management. So again, this program showed that their leak detection program had about a 5-to-1 return in energy savings versus labor and materials spent. So that does not include, reduced maintenance on compressors or increased profitability on production equipment, meaning that the reduced runtime that I may have mentioned before, or, delaying an oil change based on runtime hours, how that could be deferred. So this is just operational energy usage savings. If you wanted to try and include some of those other components in, be my guest, right? Their other main return on investment that they found was the plant's desire for purchasing new compressors in some cases. They found that fixing their leaks increased their high pressure air capacity. The plant had submitted a request for another 100 horsepower of compressor, but they didn't actually do their leak surveys prior to this. So after working with the resources and engaging their leak detection program, they were able to cancel their request, and they avoided that $55,000 cost of compressor implementation and, operational energy savings because they found all those air leaks. You want to show, again, that you want to calculate what your return on investment was. Here we do we found that the press maintenance, they found and repaired 17 leaks in this press room for a total cost in labor and materials of $1,500. What they calculated based on their runtime and the associated quantity of leaks that they were saving those leaks were costing them in this small application here was $7,000 per year. So 4.5-to-1 energy savings versus labor and materials to go into it. So I guess this just reinforces that, the energy savings are an immediate, and direct impact to the bottom line, and management can appreciate that, and they should maybe start thinking of it as an investment instead of that they should think of a leak detection program more as an investment than a mandatory cost, because it does have payback. If you have multiple plants, you might want to, look at this as a corporate initiative where you can track it from one to another and see where the severities are, see who had the most progress overall. Essentially, site performance can be rolled up to evaluate, the overall program participation. You can see where leak capture rates are efficient and effective, and maybe you can compare one site to another. Many larger sites might have this, and they can see where some of their energy usage or estimate cost avoidance is occurring. So as we kind of wrap up the thoughts of an effective leak detection program, we want to talk about the keys to success here, both at the plant and the corporate level. You'll want to have a commitment to having key personnel trained in ultrasonic leak detector use and how to enter that data into whatever tracking system you might want to employ. Not many maintenance tasks have such an attractive payback is one of the points here that we want you to take away. This program, again, should be seen as an investment and not an expense. This is definitely a component of lean manufacturing where leaks should be considered a process waste. You know, if you're thinking about all the material and all that work that you go into to reduce waste, well, compressed air can be thought of in that way too. It's not a one-time fix, right? You got to have a commitment. You got to continue looking at it. Things will change. Challenges will pop up, and so will obstacles. But you'll need to keep on evaluating your system. And sometimes you can do that in-house. Sometimes it takes another set of eyes to do that. But again, I go back to the measurement. You know, once they show management that, hey, we are saving energy, that, hey, this is the better way to do it, it kind of snowballs and goes into the next energy conservation measure. As long as you got someone who's a champion and willing to take it on. And if they're not, maybe they don't fully understand the importance or the benefit that and the time savings that it can allow them in the long run. So that can be discussed. And I guess with that, I hope I'm going to end here with just a quick thank you and to see if you have any questions and answers.
Excellent. Right. Thank you so much, Tony, for your in-depth, detailed PowerPoint. It gives people a lot of opportunity to see what the advantages are of doing a compressed air audit and how to improve their operations. At this time, everybody's unmuted. If there's any questions, please step forward to ask them at this point. Are there any questions?
One thing I'll...
Can you hear me, Joe?
Yes, correct.
Okay. Hey, Tony, a couple great webinar. I'm a firm believer in looking at compressed air efficiency opportunities because it's a win-win-win all the way around. Clearly, your slides show the value of investing in a program. If you had a couple questions, one, because some of the printing companies, you know, are not as large and maybe don't have all those resources to dedicate, what would you suggest as like a first starting point in terms of a program?
The first starting point I would say is to try and understand your system. Take some time. If you don't understand it, find someone who can help you look at it. If you don't, because you don't understand it, you can't measure, you can't manage it. It just works, right? We talked about how because we breathe free air that we think it's free, that compressed air is free or freer, and it's not.
Right.
It's an effective use. So there are opportunities and there are incentive through utility providers through the state of Wisconsin. Focus on Energy has a program where you can contact an energy advisor and get some assistance with looking at that. They have prescriptive measures or they have custom measures. So they have, depending on where you fit in to something like that, maybe you can get help if you've already discovered something you want to do. But to start, again, I would say understand your system, make sure it's operating when you need it. That is the quickest and most cost-effective application. The next is to verify your system set points, how it's controlled, and then air leaks. So go check out those air leaks. Try and find those air leaks as best you can here. Does that answer your question a little bit? Does that give some more?
Yeah, yeah. In fact, I had a follow-up question on the slide that you had, which I thought was extremely informative about the size, of the leak and the cost associated with it. Now here's a tougher question. Many times, at least from my experience, walk through facilities, doing visits at our members' operations, and you can hear air hissing. Literally, you walk by fittings or compressed air lines, and how do you, and this is the tough question, how do you equate when you hear air hissing to a size of a leak? Like, for example, the cost of leaks you have here on that slide is, I think, extremely informative, because to me, obviously that's money just going up in the air. I mean, how do you, it's hard to, I guess, without having something more sophisticated, when you hear air hissing, would it be safe to say it's almost thousands of dollars per year that a company would be losing?
Yeah. When you can hear it, you are losing that much. Yeah. If you're hearing it, that's a lot. I threw a stat out there, but I didn't put it on the slide. But approximately 80% of the air leaks that we find, you can't hear, and so that starts adding up. But if you can hear it, that is a red flag sign that your system is in that 40% or more of compressed air. The capacity of your compressed air system, you're leaking about 40% or more. So, we talked about it on this. I put this presentation on this to put it in perspective here. These 3 bars in the middle here that I talk about waste, that's just a bigger part of the pie. Yep, and it's just going up in there. So
now, if you can hear it, I was gonna say, if you can hear it, is it a 1/16 of an inch, or is it like an 1/8 of an inch, or is it a 1/4 inch, or is it even smaller? I mean, in other words, at what point when you start hearing it can you equate to that your table that you have on the size?
I would say conservatively assume that it's a 1/16 of an inch minimum.
Okay, easily. Okay.
Yeah. Good question. But again, if you can hear it, that's one thing. If you can, and again, you hear it when nothing's operating, right? When your plant's down. If your plant's operating, you're using that energy. So it's got to be when things are down.
Yeah, I mean, I've had more than one person, after I've brought that to their attention, say, hey, when we have things shut down or things are quiet, you can hear air hissing all over the place. I'm like, yeah, that's just thousands of dollars that are just going up in the air for no reason whatsoever.
Yeah. Let me go into there are like 3 different layers of trying to, maybe analyze your system, 3 different levels. The first one, and it depends on the size of your system, but there are ways to calculate your leakage rate on a whole system basis. If you were to measure, amperage and put some data loggers on the system, you can calculate how much that is. Do a pre-evaluation and then do a post-evaluation after you go and fix some things. You can see that result if you were to do data loggers or work with a third party to maybe install that and verify and manage your air compressor system. So there's opportunities there. The simple layers are a little bit less. It's a superficial view. It depends on how detailed you need to get into it.
Okay.
Yeah. Any other thoughts or questions?
I have one more, but I don't want to dominate the conversation. See if anybody else has a question. while we're waiting. Yeah, I'll wait a second. Tony, what's the cost of the ultrasonic detectors? You mentioned that there was two different types. There's a analog and a digital. Just to get a ballpark idea, if a facility wanted to purchase one of those for their system, what does that cost them?
Yeah, good question. Usually you'd want to you want to weigh it depending on the size of your system, right? Our initial we have a set, and you can rent some too. So if you were only going to look at it for a short period of time, you can find a company that rents ultrasonic leak detectors as well. But they think at budget $500 up to $1,000 for that piece of equipment, depending on if we're looking for ballpark. That's what we're talking about here.
Oh, okay. So that's not too bad. Depending upon the size of the printing operation, it might be worthwhile to invest in one, or, as you said, renting one. I didn't realize that was a possibility, because if it's
it can be.
Yeah.
If you're small and only thinking of maybe doing you're interested in doing a leak survey and wanting to do it maybe every couple of years, and maybe not as diligent as someone who does it every month or every couple months because they have a lot of components. Yeah, you could rent it.
Okay, that's a good. That's a great idea.
The value is in, of course, then the training, the man hours necessary to go find that. That's where the investment starts to increase a little bit more. But again, the investments, you get that value back at the end.
Yeah, I agree with that. That's the last of my questions. So, Joe, if anybody else has any other ones.
Are there any other questions? Well, I appreciate everybody's time today. Thank you again for presenting, Tony. We really appreciate it. That was a fantastic detail to, I think, an issue that almost every single printer in Wisconsin has. And again, I appreciate everybody participating today. Again, we'll get this recorded webinar out to all the attendees within the next few days. Thank you so much for everybody for attending.